three things that we need to accomplish. First is to find the electric field surrounding a line of charge. So let's say I have just this wire, and this wire has a charge that exists throughout the whole thing. And this charge is like this line is infinitely long, right? So, and we want to figure out, okay, well, let's say we're somewhere near this wire. What is the electric field strength that exists at some point in space, some distance we'll call A, away from that wire? Here we're going to use Gauss's law. And you should know by now that Gauss's law involves putting a Gaussian surface around a object of charge. This is something that is kind of like electric field life hack of, hey, as long as we have some symmetrically shaped object with charge, we can use this trick to get around from doing all the messy calc that we've been doing back in the first unit. So what I'm going to do is I'm going to put a Gaussian surface. A Gaussian surface is like a make-believe imaginary shape that I just put with my mind around this charge. And the idea is that if I want to know the electric flux coming out of this surface, there's two ways to do that. One, I could just simply take the electric field strength times the area of that surface, or I could take the charge that's enclosed inside that surface and divide it by epsilon naught, which is just a constant 8.85 times 10 to the negative 12. Either way, this equals what we call as electric flux. And that is Gauss's law. So for this case, this is the electric field that I'm looking for at this point in space. This area would be the surface area of the Gaussian surface that has flux going through it, and Q enclosed would be the charge that's stuck inside of my Gaussian surface. Now my Gaussian surface here is a cylinder. I put a cylinder around a line of charge. So now I'm going to plug into this equation where E is the electric field that I'm looking for, and A is the surface area that has flux going through it. If you had to draw the electric field from this line of charge, it would have arrows pointing radially out everywhere through it. And those arrows would be perpendicular, I should say parallel with the area vector. So if this is the electric field vector, this is also radially outward would be the area vector, because there is a dot product in there where these two things need to be parallel to one another. And indeed, in this case, they are. So we don't have to worry about multiplying by cosine theta or anything like that. Now I need to multiply by the area that has flux going through it. If you notice here, if I have this infinite line of charge, the line never stops, which means that I'm never going to have a field going through the ends of my cylinder. Since there's never going to be a field going through the ends of the cylinder, I should not include the end caps of the cylinder in my surface area. The surface area of a cylinder is the circumference of a circle times the entire length of that cylinder. So I'm going to multiply here by the circumference of a circle, 2 pi r, times the length of my cylinder, where I'm going to call the length of my cylinder L, and of course that radius, I already told you, was A. That's the distance that I am away from the wire. Onto this side, the charge that I'm enclosing, well, if it's an infinite wire, it's an infinite charge, but it's not infinitely enclosed. I'm cutting it off right here at this length L. But what I do have is the idea of lambda, which you all previously known as charge dq dl, or another way to write it would be the total charge divided by the total length. Q over L. Well, the total charge enclosed, if this is a uniform lambda, uniform charge distribution, then we could say that the Q enclosed is equal to lambda times L. So over here, I would have the lambda, the linear charge density, times the length divided by epsilon naught would be equal to the charge enclosed over epsilon naught. Which means that the L, or the length of my Gaussian surface, is arbitrary. It doesn't matter, it cancels out. So divide by 2 pi a, and I have my final equation. Lambda divided by 2 pi a e naught, and that will give me the electric field strength at some distance a away from a line of charge with charge density lambda. Okay, line of charge easy. Let's move on to phase 2. Because wires are not infinitely thin, if we zoomed in on this thing, what we would find is that a wire is really a cylinder itself. And we all know that when a cylinder or a wire or some sort of conductor gets charged, that charge resides on the surface of the conductor. That means that we don't have a linear charge density, we have what's called a surface charge density. Sigma is charge per area. So let's say that we have this given charge density. So I give you a charge density, and I want to know, again, what is the electric field at some point, 2 places, here and here. So I want to know what the electric field is, not only at some distance A outside of our conductor, but someplace inside the conductor as well. So I can do this using a Gaussian surface, and I can make up a Gaussian surface that symmetrically surrounds the charge that I care about. So I'm putting a cylinder around my cylinder, where the cylinder they are coaxial. That means that they share the same axis, or they share the same center. So this axis that goes through the center of my conductor is the same as the axis that goes through the center of my Gaussian surface. Again, we're going to call this a distance A away from that axis. And we'll state Gauss's law again. EA equals Q enclosed by the surface divided by epsilon naught. This A is the surface area of my Gaussian surface. So this would be E times 2 pi A L. The circle times the length, not including the end caps, because there is no field projected through the end caps. On this side, I need to find a way to get the charge that's enclosed. Well, the charge enclosed is dependent upon that sigma that I've been given. So here I could solve for that charge enclosed by saying that Q is equal to sigma times that surface area that has the charge on it. Notice that this surface area of the conductor is not the same as the surface area of my Gaussian surface, so those A's do not cancel out. And the area of the inside, the conductor, is dependent upon the actual conductor itself. I'm going to call that R. So here, I would replace the Q enclosed with sigma times 2 pi R L all over epsilon naught. The 2 pi's cancel out, the L's cancel out, and I'm left with an electric field at this point in space equal to sigma R over A epsilon naught. Now let's look at this point in space, which is inside my conductor. See, inside my conductor, I'm only a distance, let's call it b, away from the axis. But I can use this exact same process where I can make a new Gaussian surface where its surface has the is a distance b away from the center. So I'm putting a cylinder now inside of my conductor. Your Gaussian surface doesn't always have to be outside your object. Your Gaussian surface could be anywhere inside your object as well. So now I'm going to make this statement, EA equals Q over epsilon naught. Where again we have E times 2 pi BL this time, is equal to the charge enclosed over epsilon naught. But what do we know about the charge that's enclosed inside of my new Gaussian surface? There is none. All of the charge of a conductor resides on the surface of the conductor. So there is no excess charge on the inside of the conductor. So as long as I'm inside here, and this is my new cylinder that's a tube cut out of the inside of it, there is zero excess charge in there, which means that the Q enclosed is 0 over epsilon naught, which tells us that these are obviously all things that are not 0. So your electric field strength inside of a conductor is always 0. Last one. Rho. Rho is a charge, it's a volumetric charge density that is Q per volume. Is there a reason why you would only use this for insulators? Of course, we just said that if you're dealing with a conductor, the charge resides on its surface, not throughout its entire volume. So here, this must be an insulator if we're dealing with rho. If you have a conductor, you'll never go past sigma. Could be lambda, could be sigma, but it will never be rho. If you have insulators, you could have all three. You could have a surface charge, you could have a linear charge, and you could also have a volumetric charge. So let's say that I have an insulated cylinder, again, and this now has charge throughout its volume, evenly distributed so that rho is a constant number. and here's my axis of my cylinder. Again, I'm going to find the electric field in two different places. I'm going to find an electric field at a distance A, outside of the charge insulator, and we're also going to find the electric field at a point B inside of the insulator. Here, the electric field is solved the same way that we did in the last one. We're going to put a Gaussian surface around the large cylinder, around our smaller cylinder, and we'll make our Gauss's law statement. EA equals Q enclosed over epsilon naught. The area of my Gaussian cylinder has a radius of A. So this is the area that goes with the cylinder, goes with your Gaussian surface. 2 pi A L, L again being the length of it. On this side, we have the charge that's enclosed inside that Gaussian surface, which here, again, we're going to call the radius, the physical radius of my insulator, R. And now we have to find a Q. Q is not given, but rho is given. So we can solve for Q by taking the charge density and multiplying it by the volume of our cylinder. The volume of a cylinder is not the circumference times the length, but is the area of a circle times the length. So this becomes pi r squared times rho. So our Q is rho times pi r squared. Notice that this A, the radius of my Gaussian surface, is a completely different radius than the actual physical radius of my cylinder, all divided by epsilon naught. Pi's cancel out, and L, I should have length here, pi r squared times L. It would give me the volume of a cylinder. Again, neglecting the end caps because, again, this is, we're considering very, very long, and no field lines are going through the end caps. So our L's cancel out as well. And we're left with an electric field at point A of rho r squared over 2A epsilon naught. Now let's do our last bit, which is finding the electric field strength inside an insulator. And there absolutely can be an electric field inside of an insulator. There cannot be an electric field inside of a conductor, but there can be one inside of here. So here, I'm going to make another Gaussian surface, and this time the Gaussian surface resides inside of my insulator. Move over here, starting with the same setup as before. EA equals Q enclosed over epsilon naught. The electric field times the area of my Gaussian surface. Now my Gaussian surface here has a radius of B, because that's the point in space that I want to figure out what the electric field strength is. So I'm going to call that little radius B. So now we have E times the surface area of a cylinder with radius B, which is 2 pi B L. That equals the charge enclosed by 2 pi B L. I don't care that there's some pieces of the insulator that are charged that are outside my Gaussian surface. I only care about what's charged inside of my Gaussian surface, which means that when I'm switching this Q to a rho times a volume, The volume that I care about is the volume of my Gaussian surface, not the entire volume as it was when I was enclosing the entire volume. So here, E times 2 pi BL is equal to rho times the volume, which is pi r squared times L, but in this case, it's pi b squared times L all over epsilon naught. Before, these r's did not cancel. That stayed squared, that stayed in A. Now, those r's are the same and do cancel, as well as the L's, as well as the pi's. And we're left with an electric field that's equal to rho b over 2 epsilon naught. Quite a bit different than when we are outside. When we are outside, the one variable that's changing here that could potentially change outside is this, the distance we are away from the object. And as the distance that as we get farther away from the object, the electric field is only going to decrease more and more by a function of 1 over A. So what does that look like? Well, electric field versus distance away from it. Once we get to distance A away, or once we get to a distance R away, once we go past that radius of the cylinder, everything starts to decay and the electric field gets weaker as we get farther away. But here, the variable is B. This is the distance from the axis. And as we get farther and farther away from the axis, it's a direct proportion between electric field and the distance away from the axis, because you're adding more and more charge that's enclosed by your Gaussian surface. So as you're adding more and more charge enclosed, you're adding field strength. So the field strength actually grows as you get farther away from the axis, where here the field strength decays as you get farther away from the axis. So our graph looks like this. And this is an exponential decay that will decay out as r approaches infinity. Too easy.